Okay, so guys, last stuff of the unit. We have done, I think, a pretty thorough job of talking about equilibria, talking about how we describe equilibria mathematically, ice boxes, things like that. Guys, today what we're going to do to wrap all of this up is we're going to talk about one last equilibria. And these are what are called solubility products. And you'll see why we call them products in just a minute. But guys, do this with me. And I think this will be a good place for us to start. So let's take, for example, let's do this. Do this with me. So silver nitrate. Let's react that with our good friend table salt. Predict the products. So one of our products is going to be AgCl. Our other one will be sodium nitrate. All right. So now, guys, what I'd like you to do is I would like you to write the net ionic equation. You done? Because if you're not done, you should be done. So guys, in order to write net ionic equations, what is the important concept that we need to keep in mind? Spectators, which is all tied back to solubility. So, does silver nitrate dissolve in water? All nitrates dissolve in water. Does sodium chloride? Yes. Table salt. Does silver chloride dissolve in water? It does not, because the halogens are not soluble when they're bonded to silver, lead, and mercury. And then, guys, again, all nitrates dissolve in water. So because that's true, because all nitrates dissolve in water, nitrate is always a spectator. Then, finding other spectators, we know that the silver chloride has gone from soluble ions to a solid, so they're doing chemistry. They're not spectators, but we do have one other spectator. That would be our sodium ion, which started dissolved in water and ended up that way. So from this, then, we have this as our net ionic equation. Whoa, no, sorry. We have this as our net ionic equation. You okay? You're good. Okay, so guys, why did I step you through this? Here's why. This hasn't changed. This isn't going to change. For all practical reasons, this is the deal. But this is actually what happens. Guys, and again, you got to hear this. We are not changing the rules or the processes with writing net ionic equations. Does silver chloride dissolve in water? No, it is insoluble. Except for it actually does dissolve a little bit. But so small that we're going to say that it doesn't dissolve. But now we're going to talk about the fact that it does actually dissolve a little. So with that said, guys, do this with me. We're now going to talk, and all I'm doing is rewriting this, but you want to do that too. We are now going to talk about the fact that this is really what does happen. Silver chloride does in fact dissolve in water. The amount that it dissolves is so small that when we're talking about precipitation and net ionic equations, it's functionally not happening. But it does happen. So guys, here's what I need you to do. Write the Kc for this. Do it in your notes. Write the Kc for this process. You got it? You done? Let me ask you a question. When we write this Kc, this is actually not a Kc. Well, it is, but it has another name. In the same way that Ka is the dissociation for an acid. Guys, this is not Kc, this is Ksp, if you want to cross out the C and write that in. And Sp stands for solubility product. Now guys, when we say product, that is a mathematical term. What does the mathematical term product mean? Multiplication. Why do we call these Kc expressions product expressions? Because they don't have a denominator. Products divided by reactants. Silver, chloride. And guys, if you're distracted by the noises, don't. You're better than that. So guys, silver and chloride. What about the reactants in the denominator? They're a solid. This is a precipitation. That's a solid. It doesn't go in the denominator because it's a solid and therefore doesn't have a concentration. Does that make sense? Guys, that's why we call these things solubility products, because by definition, the reactant is the undissolved salt and it doesn't have a molarity, making it heterogeneous, and so that doesn't go in the denominator. That's why we call them solubility products. Does that make sense? Okay, so guys, what we need to learn to do then is we need to learn to solve these things. And you're going, oh, this won't be so bad. Guys, you have, without knowing it, been lulled into a little bit of a pattern that we've got to break. So guys, when we solve these equilibria, they're solved just like most other equilibria, except for one exception. Consider this. We're going to talk about calcium fluoride. Calcium fluoride actually is slightly soluble in water. Please, in your notes, write the equation that represents the dissociation of calcium fluoride. I'll get you started. CaF2. This is slightly soluble in water. So what does it break into? We're going to get Ca and 2F minuses. Why is this different from what you've done before? This is an acid and base. There's no hydrogen. Let me say this differently. What are you going to screw up because you've never seen this up until now? The 2. Guys, why have you never seen a 2 in an ice box before? Because all of the ice boxing that we've done has been with monoprotic acids. Let that sink in. All of the icebox problems that we have solved have been with monoprotic acids and monobasic bases. You have never seen an acid that gives away 2 hydrogens. We can't study that because they're multiple equilibria because the hydrogens don't come off with the same strength. You've also never seen a base that takes in 2 hydrogens for similar reasons. So guys, that too is going to be the death of you. Here's why. Write the Ksp. Isn't that awesome?
Hey, can I borrow the printer?
Yeah.
Give me some cycling here.
Ooh, Spandies?
Which one you want?
Bottom one. All right, so guys, let's write the Ksp. So Ksp is equal to Ca2 plus F minus, But guys, here's what you're going to find out, and I'm going to show you an example right now. That 2 will not only be an exponent, many times it's also a multiplier. So let me show you. Here we go. We're going to solve this together. Bump, bump, bump. That's everything we just did. The CaF2 is not there because it's a solid. The Ksp for calcium fluoride, check out that number. 3.9 times 10 to the negative 11th. That tells you that not much of this dissolves. The Ksp for calcium fluoride is 3.9 times 10 to the negative 11th. What is the solubility of calcium fluoride in grams per liter? How many grams of calcium fluoride can you get to dissolve in a liter of water? So guys, we're going to solve that together. Are you ready to go? Okay. I haven't printed my notes, so hopefully you guys can keep track of the number. Are we okay? Because I need a clean screen. Okay, so here we go. Let's solve this together. So we're going to write down our balanced equation. CaF2 in equilibrium with Ca2 plus and 2F minus. And guys, we're going to icebox this. You ready? This is weird. What is the initial concentration of the calcium fluoride? Doesn't matter. Look where you get to do the squiggle. Because it's a solid. So now, initially, how much calcium ion do we start with? None. How much fluoride ion do you start with? None. And now when the calcium fluoride breaks apart, how many calcium ions will we get? X. How many fluoride ions will we get? 2X. So what will then our concentration be at equilibrium? X and 2X. So now we can write our Ksp expression. Ksp is equal to calcium ion, fluoride ion squared. Was it 3.9 times 10 to the negative 11? All right. So 3.9 times 10 to the negative 11th is equal to, this is where you're going to screw it up, X times 2X, the quantity squared, which is equal to 4X cubed. Now we solve that for X. 3.9 times 10 to the negative 11th divided by 4, and then take the cube root. And I get 2.14 times 10 to the negative 4th molar. You got the receipt and stuff? Okay. Do you know the number off of here? It's 01359. Yep. Okay. But that's not the answer. So guys, let's keep this in mind. 2.14 times 10 to the negative 4th molar. And then we got to go over here. The answer says, how many grams of this will dissolve in a liter of water? So I'm going to finish this problem here. We've got 2.14 times 10 to the negative 4th moles over liters, and we want to know grams over liters. So now we need to know the mass. For every 1 mole of Ca, good heavens, F2. So calcium is 40. Fluorine is 19. Oh gosh, that didn't go well. So 78 grams. So this is 78 grams in a mole. So we have 78 times 2.14 times 10 to the negative fourth. And I get 0.0167 grams. So guys, you can functionally get about 17 milligrams of this stuff to dissolve into a liter of water. Not very much. So guys, bottom line here is these problems are very similar to the problems that we solved before. Differences include many times you will have balanced coefficients that throw off the math. Be careful. And then many times the thing that you're solving for is not the same as what the ice box produces. So in this case, we solved for a molarity, but they wanted us to convert it to grams per mole, or grams per liter. Yeah? Yeah, good question. And actually, it's funny, Emma, I was thinking, should we talk about that? And I'm glad you asked, because we should talk about it. So why does this work? And here's the answer. So this number x is this, which is the amount of calcium ion formed. But the amount of calcium ion formed is equal to the amount of this that dissolved. Can I help you make that connection? So X is the molarity of the calcium ion, but that is equal in number to the amount of these that broke apart because it's a 1-to-1 ratio. They could also ask you a question that says, what is the molarity of the fluoride ion? And in that case, you'd have to take that number and double it. Is that okay? You guys okay? Okay, so I think I probably know the answer to the question, but I'm going to go ask him anyway. I was completely unaware of this nightmare. Here, let me give you your homework. And then, guys, we're going to take a break and then come back and figure out what to do with third period. Just a second.